Hello, this is OCR Further Statistics. We're in Bivariate Data 3, Lines of Regression, and the first video, calculating a line of regression where one variable is not random. Regression analysis is used to formulate the relationship between variables. At this level, you will only be looking at linear relationships between two variables. But analysis can be done with nonlinear relationships and in multivariable situations. The non-random variable is often called a control variable. You might perhaps take readings at fixed time intervals. You are in control of those data points. In this situation, we need to have a roughly linear relationship. So this situation clearly isn't linear, so we can't calculate a regression line. The relationship looks as if it might be quadratic, which is beyond the scope of this course. Here we have a very close linear relationship, but with one outlier. We should check that result and see if it is in fact an error, so that we can remove it. And then we could calculate the regression line for the remaining data. This one is not showing any correlation. The x values are all the same, except for that one outlier. So this is a completely different scenario and not appropriate for regression analysis. And finally this one. We do not have very strong correlation here. It may be that the correlation is weak, or it may be that the measurements were difficult to take accurately. So yes, we could calculate a regression line, but we should note that the results may not be accurate. You are already familiar with the idea of a line of best fit. We could consider a line of best fit to be a visual estimate of a regression line. There are several methods for actually calculating regression lines. The one in this course, the least squares regression line, is probably the simplest. Here I've got a line of best fit drawn by I. Each of the y values has an experimental error from the value that would be predicted by this line. These errors are called residuals. So this is a residual, and this is a residual, and so on. The residuals are the observed value, take away the value predicted by the regression line. So that's R1 is equal to the observed value Y1, take away the predicted value. Note that some residuals will then be positive and some will be negative, as a good line of best fit will have roughly equal numbers of points on either side. Basically, the smaller the magnitude of the residuals, the better the regression model is. More formally, our regression line minimises the sum of the squares of these lengths. We need to square them because otherwise the negative values would cancel out the positive ones. So what we have is each of the residuals squared and added up, and we're trying to minimise that value. That's why it's called the least squares regression line. Let's see how this works in practice. Those of you who are studying physics or mechanics may recognise this as an experiment to verify Hooke's law. In this experiment, the mass is controlled, so it's non-random. Length has a theoretical true value for each mass, but will have an element of randomness to it as measured. You can calculate the equation of the regression line on your calculator. It's important that the independent variable, which should be on the x-axis, is in the left-hand column, and the dependent variable on the right. Use the two-variable statistics mode. You should get an output something like this. it will give the general equation y equals a plus bx, and then the values of a and b. Using m for mass and l for length, you can then write down the equation of the line. L is equal to 21.3, using at this point sensible rounding, plus 1.91 m. Alternatively, you may be given summary statistics rather than raw data. Here we are given the variables to use, m and l, and the summary statistics, which are exactly the same ones we get for Pearson's product moment correlation coefficient. We're asked for the least squares regression line of L on M, so we need an answer of the form L is equal to A plus BM. The required formulae are provided in the formula book. We're going to need the regression coefficient B, so we'll need SXY and SXX first. And then we'll need A. And we'll calculate that using Y bar and X bar as well as B. Note that calculating A in this way ensures that our regression line goes through the points representing the mean of the two variables. X is non-random, so is the mass. So X is equal to M and Y is equal to L. Always make a note of this so that you don't get them mixed up. We then need to find SXX, which for us is SMM. So using that formula for SXX, we've got the sum of the m squareds. Take away the sum of the m's squared over n. And then we need SML, using the formula for SXY. So we need the sum of the MLs, which is 49910. Take away the sum of the M's times the sum of the L's all over 12. Now we use those to find B. So that's SML over SMM. It's a good idea to keep the full values at this stage. Make use of the calculator memory so that you don't end up with rounding errors. And then we're going to need M bar, which is the sum of the M's over 12, and L bar, which is the sum of the L's over 12. And now we can find A. So that's Y bar. Now Y is L, so we've got L bar minus B M bar. So that's 6.241666667 minus B multiplied by M bar, which is 2.88974337. So with sensible rounding, we have that L is equal to 2.89 minus 0.00609 m. That's the end of this video on calculating a line of regression of y on x, random on non-random. In the next video, we'll look at using this line of regression.